Okay, last class we introduced the topic of induction generators, because these are now being used for generating power mainly from some non-conventional sources like wind and small hydro. In fact, there are also suggestions that induction generator can also to some extent replace synchronous generators, because you have power electronics now to control. So, earlier synchronous generators were preferred because they were constant speed. Now, even with variable speed prime movers, you can condition the power output for the required voltage and frequency using the energy controls using power electronic circuits, right. Therefore, these are some of the new features which have made induction generator more acceptable. And also induction generators have a much simpler construction compared to synchronous machines. So, that adds to the advantages, right. Okay. Now, to continue the analysis that we started last lecture, you are aware that there are two broad areas, there is a motoring and there is the generating. Motoring, the speed will be positive, slip is positive and speed is 0 to 1, okay, less than 1, and slip is negative for generating, that means the speed is more than 1 per unit, right. So, you call this speed as a V1, this is nu 1 and nu 2, okay. That is what we have done. Now, we also said that typically in the torque speed characteristic, this is the torque speed characteristics. So, you have a motoring point, operating point and generating operating point, okay. And this has a positive slip here and this has a negative slip here, okay. So, the now for this negative slip, condition, that is minus S2, okay. Now, you can call S2 dash as minus S2, okay. If S2 is negative, S2 dash will be positive, okay, just for our understanding. Now, this is the motoring equivalent circuit, right. Motoring equivalent circuit is that current Is will be flowing like this and IR will be flowing like this, okay, and IM will continue to be in one direction, okay. So, this is motoring. When do you say motoring? From the source the current is going out, that is what is motoring, right. Going, I mean it is actually not going out, going into the machine from the source, but if it is generating means the current will be going out of the source, right, that is the terminal of the generator. Okay. Supposing you neglect the core loss current and neglect the leakage reactance, for positive slip we can have neglected the, what we have done is we have neglected the rotor leakage, means this Vg and the current will be in phase, okay. Vg and the current will be in phase. So, what we have done is we have drawn Vg and the current IR will be in, this is the motoring at a positive slip, right, and then the current sorry. So, neglecting this and low slip, I think we will, okay. Now, what will be IM with reference to Vg? It will be at quadrature, right. Therefore, we write the phasor diagram. So, IM will be like this, okay. And then you know IR, what will be the IS? IS will be sum of these two. Okay. So, we have this IS and the terminal voltage will be Vg plus the drop across the resistance and the drop across the leakage reactance. Okay. So, what you finally get is the Vs, right, and the angle between Vs and Is is the angle phi s, okay, right. So, you know the power input will be Vs Is cos phi s, of course 3 times because it is a 3 phase machine, and so the from this phasor diagram you analyze. Okay. Now, when you can do this for positive S, you can do it for negative S also. That means, what changes you find from this phasor diagram if you have a negative S, which phasors will change if S is negative, the slip is negative, which phasor will change? Rotor current will be out of phase with the Vg. See, rotor current was here, then it would have gone here. See, if this is for motoring, you would have got IR for generating, is not it? Okay. Will IM change? IM will not change, right. So, then all the other things will change. So, your IS will now be at so this may be IS generating, is it right? Okay, whatever I made only changes. See, this was the motoring convention, I just change the slip. So, what do you find here? IS here, what will be the angle now? Then again with Vg plus IS, so you may have somewhere here, this will be IS RS, okay, and where will be IS XLS? Somewhere here, okay. So, you might end up with some other, I am just making this more like a dot. So, you may find Vs generating like this, okay. Now, Vs generating and Is generating will have some angle, the phi s generating, okay. I have superposed on the motor equivalent circuit, motor phasor diagram, a generator phasor diagram by just reversing IR, nothing else I have done, all other equations remain the same, okay. So, what we are trying to raise performance equations of generator with motoring conventions. It is a generator, but convention is motoring. I am not changing the conventions of what is motoring convention is the current is getting into the machine from the voltage source. Okay. So, therefore, S is S2, earlier it was S1, okay, which is negative, and of course, it is small. Why do you say it is, if S is very big, what will happen is R2 by S is small, then XR cannot be, XLR cannot be ignored, okay. Therefore, the speed is definitely more than 1, but not too much more than 1, okay. It is slightly more than 1 with maybe 5-10% in the stable region only, okay. Therefore, equivalent circuit of generating, supposing if you have generating convention neglecting IC, what will happen? Then the currents will now be like this. This is the generating convention. Have you understood what is by generating convention, motoring convention? So, the current is going out of the source. In a normal generator, you allow it to, the convention is the current is going out of the source, which is opposite to what was motoring, okay. and if it is motoring convention, then it will be this one, we have already seen this, okay, IS and IR. Okay. So, I am somehow deliberating on this because this is the very crux and central to the understanding of the induction generator. Okay. Since you have fairly familiar with the motoring, let that be the base for understanding and then build upon that. Okay. So, this is what we have done. Okay. Now, power flow, how does it happen in an induction generator? Okay. There is a prime mover which gives you the mechanical power, is not it? There is a prime mover which pumps in mechanical power. Where does it give mechanical power? To the machine? To the shaft. So, that is the mechanical power gets into the shaft. Now, but while doing it, there is also, it will take away some friction windage, is not it? Take away some friction windage, and the remaining will be the power input which is available for conversion. Is it okay? Right? Unlike in a load, so it is not a load, this is the mechanical power which is fed into the shaft from a wind turbine or hydro turbine or any other turbine, okay, or an engine which gets into the shaft. Then out of this, when it, the power which gets into the shaft to the rotor, rotor has its own losses, the rotor copper loss, okay. So, rotor copper loss is taken out. So, what is remaining, then it is available at the air gap, is at the air gap. PG is the power at the air gap, which will now through the air gap it transfers. Where does it go? It gets into the stator. Unlike in a motor where the power from the terminal gets into the stator and to the rotor. So, air gap power is opposite now. Okay. Now, from the air gap power which now transfers to the stator, and then there is certain loss in the core loss, and then there is some loss in the stator copper loss, right. So, it gets into the stator, certain loss goes out in the core loss, certain loss goes out in the copper loss, and what is remaining? Remaining goes as the power output. Where does it go? It will go to the grid, is not it? So, this is from the shaft, this is to the grid, right. I hope it is not a big deal. Is it clear how you get it? Okay. So, we will now redo this phasor diagram of generator with motoring convention and generator convention, both we will see. Okay. Now, as motoring convention we will start, we have Vg and IR is opposite to that, which we have already said, and Im is quadrature rate, that is minus j Vg by Xm. Okay. These are okay. Vg is our air gap voltage, and which will draw a current Im for magnetizing this. This Im produces Vg, is not it? And this is the IR which is due to negative slip. Okay. Now, then there is the Is will be Im plus IR, is not it? Now, what will be Is? Is will be Im plus IR, okay, and here is Is. Is it clear? I just take a sum of these two currents, whatever the rotor, because we have this circuit. So, this is IR, IR and Im, sorry, because our convention is motoring. So, this will be Is. So, Is will be Im plus IR because of the motor convention, right. Then Vs is Vg plus Is into Rs plus Jxls, okay, sorry, okay. right. So, Vs is Vg plus Is into Rs plus Jxls. So, we have got Is here and this was Vg and you add this Rs Is here, okay, and Rs XLS here, okay. So, what you get here is your Vs, is it clear? And this is all motoring equations only I am using, only thing is that current has reversed. So, you have Vs and then we said that the angle between the Vs Is is the phi s, okay. What is the angle phi s, how much is the magnitude you find? 90 degrees. So, phi s will be, you notice, is greater than 90 degrees, which will mean the power input will be negative. So, power input which is 3 times Vs Is cos phi s, which is negative, right. So, you always therefore, you must be very clear what do you mean by, you see the current, somebody says current leads, okay. In fact, current lags the voltage by more than 90 degrees, okay. Now, actually if this was the generating convention, this would have gone just other side, okay, the currents, right. So, the phi s is 90 to 180 degrees. So, Is lags Vs by more than 90 degrees, is it clear? Okay. So, active power input at the terminal of GCIG, active power input 3 Vs Is cos phi is negative. So, power input will be opposite to that of the motor. So, if you are in the motor you are putting some power input, in generator you are putting some minus power input, okay. That means you are feeding power into the grid, not out of the grid, okay. So, P will be fed to the grid from the machine, okay. Is it concept is clear, okay. And what will be reactive power? Reactive power will be 3 times Vs Is sin phi s, and which is, but this is not negative, because phi s although 90 more than 90 it is still positive. So, Q has to be fed to the machine from the grid as in a motor. So, as far as the Q is concerned, no change in direction as far reactive power is concerned from the mains, okay. Alright. So, okay, summary of okay, at negative slip S2 using motoring convention, we can write those equations very easily. So, we can write the stator impedance, motoring convention, rotor impedance, motoring convention. What will be rotor impedance now? It will have a negative real part. Stator impedance will be as it is, then magnetizing no change, okay. Then stator current you can calculate, you know the impedance, you can calculate the stator current, okay. Then you can calculate what is Vg and Vs from the same equations, right, use the same equations. Then you can calculate the no load current, magnetizing current, core loss current if you want. If you neglect IC, the no load current is, magnetizing current is this. So, these are all well known to you, I think we do not have to. So, input power factor is cos phi s, which is negative, okay. Then air gap power Pg is, what is air gap power? Whatever is the output power of P electrical plus the rotor copper, stator copper loss plus core loss, isn't it, and that will also be equal to whatever power you feed it from the turbine or the mechanical power minus friction windage minus rotor copper loss, okay, and air gap power is negative. Negative means it is going out of the rotor into the stator, right. So, air gap power Pg is 3 times IR square RR by S, isn't it. Air gap power is always 3 times IR square RR by S, which is negative, okay. So, rotor copper loss is 3 times IR square RR, which is S times Pg, but this is positive, okay. I am deliberately telling positive negative for power because you must be clear between the motoring and generating, right. So, the copper losses do not change the direction whichever way it is. So, it is always the loss, right, it does not help you. Okay. It what will it do? It goes on heating the machine, whether it motoring or generating, the losses will convert to heat wherever there are losses, okay, both mechanical and. So, mechanical losses will heat mechanical parts, electrical losses will heat electrical parts. Okay. So, therefore, the developed power is Pg minus P copper loss. See, that is 1 minus S2 times Pg, 1 minus S2 times Pg, which is 1 minus S2 times 3 times IR square RR by S2. So, when slip is negative, developed power is also negative, PD is negative. Okay. So, that means PD is more than Pg, developed power is effectively input power. In a motor, you call developed power which is getting out of the shaft. Now, the PD is negative, it is the power which is getting into the shaft from the source, from the prime mover. Okay. So, PD is more than Pg. Okay. Now, mechanical loss friction windage, which is same as per the motor, output power is PD minus friction windage. Since PD is negative, output power is positive, that means this is the input power from the prime mover, that is the P input. So, whatever is the developed so called developed power, you add friction windage. So, we have seen the power flow. Okay. Then torque developed will be whatever is the developed power divided by the speed, right, whatever developed power divided by speed, but speed is 1 minus S times omega s. So, the torque is 1 minus S2 3 times IR square RR by S2 divided by 1 minus S2 omega s, which is 3 by omega s IR square RR by S2. This is the torque in a induction generator, 3 times 3 by omega s into IR square RR by S2, okay, which is negative because slip is negative. Okay. The torque developed is negative because slip is negative. Therefore, the omega s is synchronous speed in radians per second. Okay. Then electrical efficiency will be power developed by power input, which is PD by P input, and total efficiency is power output by power input. This is a simple thing, whatever is the electrical power divided by mechanical power. Okay. Now, what is the reactive power? Q input will be 3 times Vs Is sin phi s. Okay. If S is the volt amperes at the volt amperes at the grid, V in 3 into 3 and Vs Is, and the electrical power will be S cos phi, and which is negative. Electrical power, because phi is more than 90 degrees, but Q is S sin phi, which is positive. Okay. Which is this is the power taken out of the grid and Q taken out of the grid. Okay. So, we have seen this anyway, power input, I think this is a repeat of the same thing. Okay. Power flow diagram of the generator. Okay, we have done this, I do not need to repeat. Now, if you use the generator convention, okay, you must get the same result, no, you can't have it other way around. All you have done is your current directions you have changed. Okay. Now, the IR generator is minus of IR motor. If you have generator convention, is it okay? In fact, I know since you know these currents, voltages, currents, phasors, power factor, okay, all these things and these directions of the currents and voltages, especially in AC, because these are AC systems, and this is likely to confuse any student and will drive them away from electrical engineering. Okay. But this is where you have a concept problem. So, you have voltage and current, voltage is changing with time, current is changing with time. So, we need to understand what is this power, which is positive or negative. Okay. Now, S2 dash, that is generating, is minus S2, which is nu minus 1. I have made the generating, I have made S to be negative of the motor. Okay. So, nu is 1 plus S2 dash or 1 minus S2. I have just defined S2 dash is minus of S2. Okay. Is it clear? S2 dash are defined as generating minus of S2. Okay. Then the motor current is IR as a motor is Vg by RR by S2, okay, and IR as generator is minus IR as a motor, which is minus Vg by RR by S2 or Vg by RR by S2 dash. Okay. So, that will be in phase with Vg, because IR generator is minus of IR motor, that will be in phase with Vg. Okay. So, I have made neglecting leakage again, IR will be Vg by RR by S2 dash. Vg is the reference voltage in the air gap and that is now in phase, because this is the generator convention. IR phasor is in phase with Vg. Is it okay? Whatever was there in the motor I have made just opposite to that and no change in direction of Vg. Okay. And then magnetizing current direction do not change, because that will be the same, Vg and Im will be lagging Vg by 90 degrees. Okay. Then IR will be as per generating conventions. Okay. And the IS will be, say you have, if you look at that equivalent circuit, okay, you have in generator convention your IS is here, IR is here and IM is here. So, what will be IS now? It will be IR minus IM, is not it? Okay. So, you have IR and minus IM, you know that will be here. Is it clear? Will be IS. So, my IS will be, if you look at the old one, it is just opposite to the IS of a motor. Say your IS of motor was somewhere here. This is IS of generator. Okay. So, Vs you can calculate from that, Vs will be Vg minus Is Rs excess, because Is is now getting out of the Vg. Okay. So, that will be Vs will be Vg minus Is into Rs plus Jxls. So, this is Vg, this is your Rs drop here and Jxls drop here. Okay. Is it okay? So, you have got the Vs here. Now, what is the angle here now? Vs to Is is this angle, right, and that is why they say Is leads Vs by phi s, because see this is a very confusing concept per se, because suddenly I say you know it is leading current simply because it is generating convention. Okay. So, obviously, the what is Vs Is cos phi is now the it is the power output now, is not it. So, we observe that phi s is 0 to 90 degrees, earlier it was 90 to 180 degrees. Okay. So, Is leads Vs by phi s, which is less than 90 degrees. Okay. Right. So, active power output at the terminal will be P out is P electrical 3 times Vs Is cos phi s, which is positive now. By definition it is positive, and P will be fed to the grid from the machine. P is fed to the grid from the machine. Okay. Then Q out will be 3 Vs Is sin phi s, which is positive and leading. So, GCIG feeds leading var to the grid, right. GCIG feeds leading var to the grid means GCIG absorbs lagging var from the grid as in the motor, there is no change, right. I think these terminologies are likely to can be very easily used to confuse the students and ask some viva questions like this. Okay. Feeding leading var, absorbing lagging var, okay, right. So, these questions are likely to for any interviews you may find such questions are asked and people can be made to be confused. So, you please understand a grid current induction generator feeds leading var to the grid as per VSIS sin phi s, means it takes lagging var from the grid. Okay. Right. So, I think sorry. So, performance equations we summarize: stator impedance as same as motor, okay. Rotor impedance S2 dash is positive now, right. S2 dash is S2 because it is S2 dash. Magnetizing impedance same as motor, okay. I am writing the equations in the generating mode, okay. Then equivalent circuit Vs plus Is Zs plus Im Zm is 0, or Is is equal to Ir minus Im Zm as Ir Zr equal to 0 from the equivalent circuit. Then Vs plus Is Z equivalent. So, you can find out what is the Z equivalent from the equivalent circuit. This equation Vs plus Is Z equivalent. See, if you look at the machine, this is your Vs, which has not changed direction, your Is is here, and this is Z equivalent. Okay. So, you have Vs plus Is Z is equivalent is 0, unlike in a motor which is this is minus. Okay. So, Is is minus Vs by Z equivalent. In the generating convention, the stator current will be minus Vs by Z equivalent. Okay. Air gap voltage is Vg equal to whatever is the or Es is Vs plus Is Zs. Whatever Vs plus Is Zs is the Vg, because Is is now coming out of Vg, right. No load current you can find out I naught, Im, Ic, because you know Vg. Then power flow will be, sorry, okay. So, you can find out IR, you know Vg and Zr, you can find out IR which is Is minus I naught as a generating convention, right. Input power factor is cos phi s, and phi s is the impedance angle of Z equivalent, that is tan inverse x equivalent by, how do you find phi s? You know Z equivalent, its angle is phi s, is not it. And power flow, output power P electrical is 3 VSIS cos phi s, and stator copper loss is 3 IR square Rs, rotor copper loss is 3 times Vg square by Rc. I mean, this is a standard equivalent equations similar to a motor. Air gap power Pg is P out plus P Cus plus Pc, that means whatever output power that it feeds to the grid plus stator copper loss plus core loss is what is coming out of the air gap, and that will be equal to what is mechanical minus friction windage and PCUR, this we have already seen. Okay, air gap power from rotor to stator. So, Pg is 3 times IR square RR by S2 dash is minus 3 times IR square RR by S2 dash, actually there is a S2, okay. Then it is copper loss is 3 IR square RR, and P mechanical is this we have 3 IR square RR 1 by S2 dash plus 1, and torque will be PD over 1 plus S2 dash omega s, that will be 3 by omega s IR square RR by S2 dash, okay. This is the torque, right. Output power electrical is of course 3 VSIS cos phi, of course this is again it seems to be repetition, phi s is less than 90 degrees. Okay. Reactive power 3 VSIS cos phi is positive leading and negative lagging, okay. So, GCIG draws lagging var from the grid, okay. This again we are repeating the same thing. Okay. So, this is a power flow you are feeding to the grid, right. So, P electrical or P out you are feeding to the grid, right, and the power input is from the prime mover here, okay, and then friction windage you have P mechanical which you are feeding into the grid into the machine. Then after the rotor copper loss here you have the Pg, okay. Then of course you have certain losses here PCU S and PC, then you have the feeding, okay. Right. Now, if you want to compare stator voltage, motor and generator, I am just comparing. Stator voltage same, no change, agreed. Stator voltage, grid voltage is same. Stator current in a motor it is Is, in generator is minus Is, okay. Magnetic current same, Im and Im. Air gap voltage is same, no change, okay, just comparing. Okay. Right. Now, rotor current IR here, generator it is minus IR here, okay, IR and minus IR. Then slip is S here, this is minus S here, this is opposite, right, that is our S dash you can say. PG air gap power 3 times IR square RR by S, and this is 3 times IR square RR by S dash, right, which is opposite to this, okay. Now, shaft power, in the case of motor it is output power, in the what is shaft power is output power in the case of motor, that is this 3 times IR square R by S into 1 minus S, right. But in the shaft power here is input power which is opposite to the this power, okay, that is 3 times IR square RR by omega S into RR by S dash, because S becomes S dash and this is 1 plus S dash here, that will be the shaft power, okay. Developed torque TD is 3 times IR square by omega S RR by S, this will be the torque developed in a motor, and the torque developed in a generator will be minus 3 times IR RR A square RR by S into omega S, which will be 3 times IR square RR by S dash into omega S, you know S dash is minus S, okay, and speed is 1 minus S here and here is 1 plus S dash, right, S dash is negative slip, okay. Right, and mechanical power in this case 3 times IR square RR by S into 1 minus S times that, and here it is 1 plus S dash in generator mechanical power, right. Electrical power is 3 times VSIS cos phi S, and here also 3 times VSIS cos phi S, which is negative of this, okay. So, these are the expressions that you should know for motor and generator and knowing and taking appropriate values of slip, okay. Right. Now, whatever we have done we have graphically shown here. So, in a motor you have P electrical, you have the PG, okay. From here PG you have the P mechanical, you have the torque, speed, load torque, right. This is the developed torque TD which will be in the same direction as speed, okay. Developed torque is same direction as speed and the load torque opposes the developed torque. Load torque opposes the developed torque and load torque is opposed to the speed, okay. So, the P mechanical power is going like this, okay, and this will be the output power which is goes to the load, this is your mechanical load, this is the motoring. Now, let us look at the generating here. the difference is P electrical has now it is feed to the grid going out, and this is the P mechanical or P input, right, and here is the P mechanical direction, and it is producing the torque input. This is the torque input. What the turbine does, it gives a torque to the generator, okay, and that will drive the speed. So, T input and speed are in the same direction, okay, but the developed torque is opposite to T input. So, developed torque is opposed to speed. Developed torque, like a back EMF in electric, developed torque is opposed to the speed. Speed is in the same direction as input torque, okay, and then you have the PG, okay, then it converts to P electrical, okay. Is it clear? What will be the flow of power from the motor and the generator, okay. Right. Now, same thing we will let us look at how actually it is, what are the practical cases when the system is used for the grid, okay.
Excuse me, sir.
Yeah.
What is the function of capacitor there? Capacitor in our entire analysis.
We have capacitor, you just put it in the terminal. So, it will draw a current IC. So, the output power to the grid will be whatever the stator power, stator current, output current to the grid will be stator current minus capacitor current.
So, what will be the use of by placing the capacitor in our analysis?
Yeah, we will see that now. What will be the use of placing the capacitor now? Okay. Now, if it is wind driven machine, see induction generators are used because for low and medium power generation, because they have certain advantages. What advantages are there compared to a synchronous generator alternator? Low unit cost, for the same power it costs less, okay. Then less maintenance, and it is rugged and brushless rotor, and you do not need to synchronize. The great advantage is no synchronization is required. For synchronous machines you should do a synchronization, right, you must run it to the same frequency and do the thing. Here you do not have to bother about it, okay. You can start it as a motor, run as a generator, okay. So, these are the advantages of, you must remember this at any time, okay, because I tell you, if you talk to someone on induction generator, the next question he will ask you is why you go for induction generator, okay. Now, this is the this answer this question. This is the prime mover which can be a turbine, induction generator. Now, you have put a capacitor now, right. It can be an HT side or LT side of the transformer. This is a transformer and this is the grid. So, my grid is not just at the generator terminal, a grid is away from generator terminal. You see, yesterday I showed you the windmills. See, after all, generator is just sitting on the nacelle. From there a long cable will come, and below there is some capacitor control circuit, then you have a transformer, and then only you connect to the grid. This is the grid where the voltage and frequency are maintained, right, because this itself is a weak grid. So, how do you for analyzing this, not all this equivalent circuit, you must take the system parameters. System parameters is the capacitors, transformer impedances and transmission line impedances. They will all come into the picture, is not it? So, if you want to write an equivalent circuit of induction generator with all these parameters, your S is negative node, this is your generator, okay, your RS, XLS. So, this is your generator, but then you have the capacitor at the HT and LT side of the transformer. You can either have it both sides or one side depending upon the planar. Then you must write the transformer impedance. Transformer also has resistance leakage reactance, okay. Then you must transmission line also, I hope you know transmission line also has its reactances, okay, and there is also a grid also has a system reactance. I think there is nothing like a ideal grid. What is a grid? Grid is a voltage source with its own reactance. I hope you have studied this somewhere, right. Even a battery you can't say by an ideal source, you put some resistance to represent. So, your system study will have all these things. Okay. Now, your input power coming from the turbine will be minus 3 times IR square RR by 1 minus S by S. Since S is negative, input power is positive. So, you know what is the power that is coming out of the grid, right. This is the power that you are, this is all you know, okay, and this is the power which is coming from the turbine. You know this power, okay. I have put say 500 kilowatt, 600 kilowatt. As the wind speed changes, this goes on changing, but you should know what is the slip and what is the current. You do not know what is IR, you neither know what is S, right. So, how do you find that? These are two things, okay. So, you must find the response at constant power, because this is all you know, okay. So, what you do is simplest what we did was use a Thevenin equivalent circuit. Now, how do you do that? So, the Thevenin, what is this is one RR by S is there, all other things you take it as Z Thevenin, you can do that, you can do Z, this is the only which is variable, and V you have V Thevenin. Is it okay? From that equivalent circuit write an Thevenin equivalent circuit, okay. Then you have the power input, minus 3 times IR square RR by this, you know this equation, power input, and you know the Thevenin equivalent circuit, it is simple, I am just writing a Thevenin equivalent circuit. And what are the unknowns here? S and IR, is not it? Two equations, two unknowns, okay. So, you can hopefully, so from this figure you can find out what is IR, okay, V Thevenin divided by this, okay, and this is a sort of a equation you will get A square plus BS plus C, where these are the constants A, B, C in terms of the Thevenin parameters, and V Thevenin, power input, okay. I mean this is RR square actually. Actually, I will give you a reference in the next class. There is an IEEE paper which we wrote, right, where this is explained, right, okay. And so, what you can do is from this simple, it is not so simple, you have to develop a computer program for this. You can study the effect of variation. What we did was, there was a question posed to us some time ago, that what will be the effect of grid variation. Grid voltage is not fixed, okay, it varies. Your wind speed is fixed, right. If grid varies, will it give the same power? Will it give the same power? So, and if grid frequency varies, what will happen? So, we did a study on what is the effect of grid frequency, okay, with varying grid voltage in what will be the current, this will be the current, and this is the slip, okay. These are some of the characteristics which can be from the equations which I just narrated, it is possible to do, okay. Then you want to know what is the capacitor that you connect, right, and now we discovered that our 0.6 pu is a good value of capacitor to go. That means what is the effect of variation of capacitor with the performance of the machine at any given input, even if a constant input power. So, there will be variation. So, there will be, this will be the generator current, and this will be the system power D somewhere here, this is the system power, these are some variations, okay. And this is the H is what, reactive power, this is Q. So, what you notice is reactive power, if it is there, if you do not connect any capacitor, it will draw a large reactive power, and if you connect 0.6, there is no reactive power drawn from the grid. So, you can control the reactive power drawn from the grid by connecting suitable values of capacitors. So, that is what this is very important study which was made, okay. And this is the effect of, if your wind speed changes, if there is a power input variation, then all these things will change. This will be the with and without capacitor. These are some of the curves. We have what is the machine current, what is the machine efficiency, what is the power fed to the grid. See, for example, C is the power fed to the grid, okay. I think it is this, okay. Then the slip and the current, this is the system current, var drawn from the grid, that is this one, this is the var drawn from the grid, okay, and this power factor at the grid, that is the G, this is the power factor at the grid. So, you will notice that with and without capacitor, this is, with capacitor is this dotted line, without capacitor is that full lines, okay, and these curves are given in that paper. I have just reproduced from there, maybe you can, I will give you a copy of the paper, you can see that one, okay, right. This is the effect of power input, again the same thing, you know, I think it is for another machine, 11 kilowatt machine, okay. So, we will close here. So, what we have covered is quickly to sensitize you on induction generator, especially wind and hydro systems, how it can be used and what is the effect of these various parameters, and this would also require you to read more, okay. This is, we will close it here now, okay.